This is the first lecture on digital electronics and computer organization. And in this lecture, we are going to deal with number system. A number system is defined as a system of writing to express a number. A number system is a mathematical system with base n, where n represents the total number present in that system. For example, in the case of a decimal system, the total number of digits are 10. Okay. Now, radix point. We are discussing some basic definitions and basic preliminaries which are required to understand the number system. First is radix point. Radix point is a base point used to separate the integer part and the fractional part of a number. For example, when in the lowercase, it is shown that integer part and the fractional part, and there is a point between them that is known as radix point. Base or radix. The number of symbols used in a number system is called base or radix of the number system. For example, in the case of a decimal system, the base is 10. For a binary number system, the base is 2. For a hexadecimal number system, the base is 16. Most significant bit, that is known as MSB. The leftmost bit of a binary number which has the highest place value is called most significant bit. Similarly, least significant bit, the rightmost bit of a binary number which has a least place value is called least significant bit, LSB. Bit, it's a binary digit. Any binary digit is called a bit. For example, 0 is a bit, 1 is bit. Nibble is a group of 4 bits. For example, 0, 1, 1, 0 or 111, 0. These are nibbles. Byte, it is a group of 8 bits. Examples are given below that. For example, 0, 1, 1, 0, 1, 1, 0, 1. These are total 8 bits. Therefore, it is a 1 byte of instruction. Okay, now let us come to the number system. In general, a number system, in a system having a base or a radix r can be written as an minus 1, an minus 2, up till a naught. Then there is a radix point, and a to the power minus 1, a to the power minus 2, and till a to the power minus 1. This will be interpreted as, for example, y equals to a n into r to the power of n plus a n minus 1 into r into the power n minus 1 plus a n minus 2 into r to the power n minus 2 and so on, where y is the value of the entire number and an is the value of the nth digit and r is the radix. This can be more easily understood when we go to different number systems. Let us first of all see the decimal number system. Total, we will be studying about 4 number system: binary number system, octal number system, decimal number system, hexadecimal number system. Now, first of all, let us see the one of the basic decimal number system which we use in our daily life. The decimal number system contains 10 unique symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. In decimal system, 10 symbols are involved, so the base or radix is 10. It is a positional weighted system. The value attached to the symbol depend on its location with respect to the decimal point. Let us see by an example by its general definition. In decimal number system, we start with d to power n, not power, dn, dn minus 1, dn minus 2 up till d naught dot, there is a radix point, d minus 1, d minus 2, d minus up till d minus n. Okay, now this number can be its value can be given as dn into 10 to the power, because its radius is 10, dn into 10 to the power n plus dn minus 1 into 10 to the power n minus 1 plus dn minus 2 into 10 to the power 9 n minus 2 plus so on up till d0 into 10 power 0. And for the numbers below the radius point, it can be given as d minus 1 into 10 to the power minus 1, d minus 2 into 10 to the power minus 2, plus so on up till the d minus n into 10 to the power minus n. For example, I'm taking an example for the 9256.26. It's simply 9 into 10 power 3. Okay, because it's at the fourth position from that radix. The fourth position is nothing but 0, 1, 2, 3. 9 into 10 to the power 3 plus 2 into 10 to the power 2 plus 5 into 10 to the power 1 plus 6 into 10 to the power 1 plus the decimal numbers after the radix points is 2 into 1 10 to the power minus 1, 6 into 10 to the power minus 2. In this way, you can expand a decimal number. Now, similarly, let us see what is the binary number system. The binary number system is a positional weighted system. Again, it has a radius of 2. There are two independent symbols, 0 and 1. A binary digit is also known as bit. The binary point separated the integer and fraction point. Okay, the radix point. Again, this can be written in a general way: dn minus 1, dn minus 2 up till d0 dot d minus 1, d minus 2 up to d minus k. Again, if it is expanded in general, it is given as dn into 2 the power n, dn minus 1 into 2 power n minus 1, dn minus 2, and so on up till radix point. And below the radix point, it will be d minus 1 into 2 with the power of minus 1, and d2 with into 2 power minus 2, d minus k into t 2 to power minus k, and so on. Similarly, if we go for the octal number system, it is also a positional weighted system. It has a base or radius of 8. It has 8 independent symbol from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7, 7. Okay. The next system is hexadecimal number system. The hexadecimal number system is again a positional weighted system. It has a radius of 16. The symbols used are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And after 9, A, B, C, D, E, F. So, now let us see conversion. Conversion of one number system to the another. In this series, we will be doing starting with the binary number system. The first conversion that we are doing, that is binary to decimal conversion. In this method, each binary digit of the number is multiplied by its positional weight, and the product term are added to obtain a decimal number. Let us understand it by an example. Now let us see that we have to convert 10101, which is in the binary, to decimal. Now the respective positional weight are given on the 10101. that is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. So by multiplying the binary number to the positional weight and adding them, you will be getting 1 into 2 to the power 4 plus 0 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. So for the first part, you will be getting 16 plus 0 in the second case. For the third case, 1 into 2 to the power of 2 will be 4 plus 0 into 2 to the power of 1 will be 0, and 1 into 2 to the power of 0 is 1. Adding this up all them, you will be getting 16 plus 4 plus 1 equals to 21. This is the decimal conversion of this 10101. Similarly, let us come to the second example. Second example is fractional, having a fractional part 2. Here you can see the conversion is 1.1, 100, again, 111.101. Now, again, taking the positional weight of 1 into 2 the power of 2 plus 1 into 2 the power of 1, 1 into 2 the power of 0 plus the binary numbers on the left hand side of the decimal will be taken in the with the negative positional weights, 1 into 2 to the power of minus 1, 0 into 2 to the power of minus 2, and 1 into 2 to the power of minus 3, which will yield you with 4 plus 2 plus 1 plus 0.5 plus 0 plus 0.125, which can be added up to 7.625. So in this way, you can convert a binary number to the decimal number. Now let us see the next part, a binary to octal conversion. For this conversion, binary to octal, you have to, the binary number are divided into group of 3 bits each, starting at the binary point and proceeding toward left and right. For 0, the binary 3-bit binary is 0001. For 1, it is 001. For 2, it is 010. For 3, it is 011. For 4, it is 100. For 5, it is 101. For 6, it is 110. For 7, it is 111. Now, let us understand it by an example. Let us, we have uh, uh, the binary number shown over here, which is 1 0 1 1 1 1 0 1 0 1 1 0 and so on. Now I just simply doing I'm just taking a combination of 3 bits from the point. Combination of 3 bits. First combination is 110, then after that it is 010, then it is 111, and so on, 101. Now, and after the decimal, again I am taking 110, 110, and 011. Now, write the respective octal part of this. 110 is nothing but 6, 010 is 2, 111 is 7, 101 is 5. Similarly, after decimal, 110 is 6, 110 is again 6, 011 is 3. So the conversion is 5726.663. Now, similarly, we can go for the second example. Now, if you are going, you can see here that when you are taking a combination of 3 digits, 1, 1, and so on, last we are left with the 2 digit. Then in that case, the default you will be taking 0 over here. And similarly, in the last, if there is 1 bit or 2 bit left, you have to take default 0 at the end. Okay, after doing this, again take the octal part of this 001 as 1, 111 as 1101 as 5, 010 as 2, 011 as 3, 100 as 4. the conversion of this binary number will be 2571.34 in the with a base of 8. Now, let us see how can we convert a binary to an hexadecimal conversion. Similar to the octal part, we will be making here the combination of 4 bits in the case of hexadecimal. Now we'll first of all take a see that what are the equivalent of 4-bit binary. 40 is 0, 0001 is 1, 0010 is 2, 0011 is 3, 0100 is 4, and so on. And after line 1001 is 9. For 1010, which is whose decimal equivalent is 10, but in the hexadecimal case it is A, then B, then C, then D, then E, then F. So these are the 4-bit binary equivalent of hexadecimal numbers. Using this as your base, now you will be converting the entire binary number into hexadecimal number by taking a pair of 4 bits and writing the equivalent hexadecimal number. Let us understand it by an example. For example, here is that we have to convert 1011 011011, which is a binary number, into hexadecimal. Now I'm from the left hand side. I would like to start from the right hand side. I would like to start 1011 4-bit, then again 1101 another 4-bit. Now we are left with the 2 bits. Then in this case also we will be taking the default 2 zeros. Now 1011 is nothing but B, 1101 is D, 0010 is 2. So the conversion of this binary number is 2 dB in the hexadecimal case. Now let us see a fractional number 2. Here also, as in the case of octal, we similarly here also we will be taking a combination of 4 instead of 3 for the hexadecimal case. We will take 1011 the first combination. First combination from the point here. Take a 4 digits, which is then next 4 digits, 4 times ones. Then we are left with 010. In this case, take a default 0 over here. After decimal, again take combinations of 4 bits, 0, 111. Then we are left with the 2 bits, 11. So in this case, you can add 2 more 0 as a default part. Now convert this 4-bit binary into equivalent hexadecimal. That will give you B, F, 2 point and after 0.7 C. So the hexadecimal equivalent of the given binary digit is 2FB.7 C at the base of 16. Now, this was all about the binary conversions, binary to decimal, binary to octal, binary to hexadecimal. Now let us see in the case of decimal number system. Now I am going to do the decimal to binary, decimal to octal, and decimal to hexadecimal. In this series, first of all, let us see the decimal to binary conversion. In the conversion, the integer number are converted to desired base using successive division by the base or radix. So we will be using here the successive division method, in which we divide the number which is to be converted to binary by the base radix, that is 2. So we will be continuously dividing, and the remainder will be used as 0 and 1. Let us see in an example here. We are going to convert 52 into the binary number. So we are dividing it by 2. We are getting 26. In this case, the remainder is 0. Again, we are dividing it by 2. 13 it goes by 13, and the remainder is 0. Then again 2 6 12. remainder is 1, 2 3 just 6, remainder is 0, 2 1 2, remainder is 1, and finally the remainder is 1. So from downward to upward, we will write the binary equivalent of 52, that is 1 1 0 1 0 0. Now let us convert a fractional decimal number into binary. Now, for the in this case, we will take the integer part 105, and we will be again doing the fractional division as we have done in the previous example 252. You are getting 1 as a remainder, 226, 0 as a remainder, 2 in 13, 0 as a remainder, 26, 1 as a remainder, and so on. And you are finally getting 11001. This is the binary equivalent of the integer part. Now for the fractional part, we simply do a simple method. We just take the fractional part and multiply it by 2. Multiply by 2 and you are getting 0.30. We again going on multiplied by 2 uh, until we get the final answer as 0.6. Then 0.6 into 2, you getting 1.20, 0.20. Now, when as soon as you get the 1 in the integer part, you just keep the integer part, and the rest of the fractional part is again multiplied by 2. So 0.40, 0.40 into 2 is 0.80. If it is repeating again the same integer part, as we can see over here that 001, and it is again repeating 001 as an integer part. So in that case, there is no requirement of again multiplying again and again. As soon as we, or otherwise, as soon as we get the 1 as an integer part and 00 as a fractional part, we stop multiplying it with the 2. Now, in this case, as it is repeating again and again, so we can simply uh, take the integer part of the this multiplications and write it as a fractional part of the decimal, as shown in the example. Now, decimal to octal conversion. To convert a given decimal number into octal, successively divide. Now, it's again the same as in the case of binary. We were dividing it by 2. Now, in this case, we will be dividing it by 8. Okay. We will be doing the success. For example, this is 378.93. We are dividing 378 by 8. We are getting 47, and the remainder is 2. When it is divided by 5, the remainder is 7. When it is multiplied by 0, and the remainder is 5. So the integer part is 572. Now for the fractional part, again the same method as we have done in the uh, binary part. 0.93 into 8, that is 7.44. Again, as soon as we get the integer part, we take the fractional part in the next step and multiply it by 8. You get 3.52. Again, we will taking 0.52 in the next step and multiply it by 8. You will getting 4.16, and so on. And now, considering only the integer part as the as a octal conversion of the fractional part, we can write it as 572.7341 as a octal conversion. Now, decimal to hexadecimal. Again, it is having a base of 16. So we are, in this case, we will be doing the successive division by 16. And with the same procedure, for example, 2598 is divided by 16. The portion is 162 and the remainder is 6. 16 multiplied by 10 is 160. The remainder is 2. 16 10 160, and so this is 10 to 6. The 10 can be written as A A to 6, and for the again for the fractional part, we are going to multiply it by 16, and doing the same procedure as for the octal and the binary part. We will just take the all the integer part of this multiplication and take it and convert it to the hexadecimal. 10 is represented as A and 12 is represented as C. So you are getting A to, this is the integer part, A to 6 point A, C, C, C. Now, let us move toward the octal number system. Now, we will be doing the octal to binary conversion, octal to decimal conversion, and octal to hexadecimal conversion. So, given now to convert an octal number to a binary number, it's very simple. Just replace each octal number by a 3-bit binary equivalent. For example, if this 367.52, so the octal part will be simply 7 can be represented by triple one, 6 can be represented as 110, 3 can be represented as 011, and for the fractional part, 5 can be represented as 101, 2 can be represented as 010. So the binary equivalent will be simply this combination. You will just sum up this combination and you will getting the answer 0.1111011.101010. So octal to binary conversion is very simple to do. Now octal to decimal conversion. Octal to decimal conversion. For conversion the octal to decimal number, multiply each digit in an octal number by the weight of its position and add all the product term. Simply 4057.06, in this case 4 into 8 power 3, 0 into 8 to power 2, 5 into 8. Just use the positional weights and multiply it by the positional weights and just add up them. So you are finally getting uh, uh, the decimal conversion of the octal number. Octa to hexadecimal. For conversion of octal to hexadecimal, must convert the octal number to binary. Okay, by simply taking the 3-bit digits. For example, this 756.603 is first of all is converted to uh, three each octal digit, 110, 101, and so on. Now convert now make it a group of 4 bits now. Just make it as a group of 4 bits. For example, if this is 110, take 1 from here. You get a 4 digit over here, 0, 1, and 2 ones from here. So you will get a 1110, and only single one will be left behind. Take it with 3 zeros. Now convert. Well, first of all, you have to take a 3-bit, then pair them as a 4-bit, so that we can write a hexadecimal equivalent of that. So in this way, we can convert an octal to a hexadecimal part. In this case, I'm just repeating. First of all, convert the binary number, octal number into a 3-bit binary, as we usually do. Then this 3-bit binary, sum up them and make a pair of 4-bit binaries out of that. And that 4-bit binary can be easily converted to the hexadecimal number. Now, let us come to the next hexadecimal number system. Now, I am going to convert the hexadecimal number system to binary, hexadecimal to decimal, hexadecimal to octal. Now, hexadecimal to binary is again very simple. Take if there is any hexadecimal number, consider each hexadecimal number and convert it into a 4-bit binary. For example, here 3A9E point B0D. Now, E is having a 4-bit binary equivalent as 1110, 9 as 1001, A as 1010, and 3 as 0011. And similarly, B can be written as 1011, 0 can be written as 4 times 0, D can be written as 1101. Now combine this whole, which will give you the binary conversion of the particular hexadecimal number. Now, hexadecimal to decimal, it's again simply positional weighting of doing weighting the hexadecimal number. For for example, A0 F9.0 EB. Now, A is at the fourth position, and A is represent 10. 10 into 16 power 3, 0 into 16 power 2, and so 15 into 16 power 1. Just simply just multiply by the positional weight and sum them up. You will be getting the answer. Now, hexadecimal to octal conversion. Hexadecimal to octal conversion is similar to the octal to hexadecimal conversion. Only the difference is that here the hexadecimal number is first converted to a 4-bit binary. Then we just bunch them up and do the 3-bit binary pairing and take out the octal form of from that. For example, here B9F.AE. Now, B can be for a 4-bit binary, it can be written as 1011. 9 can be written as 1001. F is 111. A is 1010. E is 1110. Now, after getting this, now I just take 3 bunch. First 3 bunches, 111, then 1, 1, 0. Then we are left with 0 here, 1 here, and another one from here. Okay. Then rest is 101. Now I'm just simply making a bunch of 3 bits. Similarly, in the fractional part, I'm taking 101 here, and then 0, 1, 1 here, then 1, 0, and default it will be taken as 0. Now, this 3-bit binary is converted to, it is done a octal conversion. 101 can be written as 5, 110 is 6, 011 is 3, 111 is 7, and so on. And in this way, you get an octal conversion for a hexadecimal number. Okay, with this, I conclude this lecture. Here we have seen the different number system. How can we convert a one number to one number system, one number from one number system to the another one? In the next lecture, we will be seeing about different codes, binary codes, and different codes which are used in the digital system. Till then, goodbye.